Canvas web page.
Yeah.
I want to show you something. On the top here, to log on to Zoom meeting, that link is there. All right. You guys always ask me what is the link, and some people haven't got it. They complain. Sometimes you don't check your email, what is in the Canvas. You need to check your email where I only send it to email that appear on the Canvas course page, official email address. Okay, so we're going to start on module 2. We finish chapters 1 and 2, module 1, and took the test last class period. Okay, so we're going to start on module 2 for test 2. So if you go to the module 2, like you've seen in module 1, chapter 3 resources and chapter 4 resources appear. So that's where you should be looking at now. So you have chapter slides, chapter quizzes, instructional objectives, and details that you need to read to get more information. All right, I'm going to start on chapter 3, PowerPoint slide today. I'm going to close this window and then go to the PowerPoint slide. See my PowerPoint slides for chapter 3. Okay, I assume that you can see. All right. Okay, I'm going to start the PowerPoint presentation. We're going to have a second test on somewhere around October 6th. So it can change. I will send you email with the announcements. We're going to cover chapter 3 and 4 during this presentation, with the activities in module 3. Chapter title is Radiation from Sun. Okay. So we're going to look into certain things to describe the material that we need to cover. Radiation from sun is an important part of our lives. Of certain radiation, sun's energy coming from sun is made out of certain electromagnetic radiation. So we're going to discuss about electromagnetic radiation. We're going to discuss different radiation like infrared, visible light, UV light that are found in the electromagnetic radiation. Different radiation have different properties. Ultraviolet radiation is important. It causes damage on the skin. There are 3 ultraviolet radiations that we need to discuss: ultraviolet A, ultraviolet B, and ultraviolet C. A is the one that passes through the atmosphere and fall on our skin and can cause damage. So biological effect of radiation is it causes skin damage, skin burn, and cancer also a possibility if you are exposed to ultraviolet radiation. We're going to talk about them. Atmosphere is protecting us from certain radiation like UV radiation. So we're going to discuss about mainly stratospheric ozone layer, how it protects us from UV light. The ozone is the protector in stratosphere. So we had to know how to count molecules and measure ozone level concentration in atmosphere. We're going to discuss about how to measure concentration of ozone. So we also going to look into the ways that UV light can decompose in the stratosphere. Is it safe? Ozone layer is destroyed by coolant in air conditioners, freon like substances. So we found out ozone layer is being depleted. Then chemist and the chemical industry came to the rescue. There was a hole in the ozone layer. We're going to look into that caused by depletion. Can we restore the ozone layer? We're going to discuss about that. So finally, we going to look into certain things that we do to protect from sunlight, like sunscreen, wearing clothes, hats, etc. So this is the topics we're going to cover in this chapter. What is sunlight and what are its properties? Sunlight is mainly electromagnetic radiation. It passes through the vacuum in the space between sun and the earth and enter atmosphere. How does different radiation define energy? Energy-wise, ultraviolet is high energy than infrared. Infrared is thermal energy, which is conducted. Thermal energy radiated from sun is infrared. That's lower energy than UV light. We're going to look into link between sun exposure and skin cancer. How does Earth atmosphere naturally protects us from sun? So we're going to look at the ozone layer and how radiation is absorbed from the atmosphere. The protection, natural protection is ozone layer in the stratosphere. Can we restore it if it is eliminated? So some of it is eliminated. Now we have come up with ways to restore the sunlight. How does sunscreen blocks radiation? So we're going to look into these things. The video on the link below, go to the PDF file of the PowerPoint presentation. You can click on that link and watch the video. So you can look into different ways you can protect from sunlight while you're in outdoor on a sunny day. This is your turn. Sun's damage. You get to start thinking about sun and damage it can cause. You can discuss with other people what is emitted from the sun. Radiation, thermal radiation, UV radiation, other radiations. What do you think about exposure can cause damage? Cancer and skin damage, mainly. Cancer. What are some of the positive effects of sun? Can you think of positive effects of sun? Suns provide visible light that keep us daylight, and it also absorbs emit visible light that participate in photosynthesis to produce our food. Also, there are, make sure that you don't make noise, okay? Suns have positive effect. What is in the electromagnetic radiation that come from sun? Electromagnetic radiation is waves composed of electric and magnetic field that travels through empty space. It don't need a medium. Like water waves need water, but electromagnetic radiation pass through space. This radiation could be visible and invisible. This prism in here breaks it up to sun's radiation into visible region. There are radiation on the top and the bottom of the red and the violet region that you cannot see. So these things are explained in here. Infrared light appear above red light is low energy. Visible light is a mixture of different colors, VIBGEO, violet, indigo, red, green, yellow, orange, red. Ultraviolet light is after purple, violet color is bottom of the electromagnetic spectrum shown in here. Microwaves appear on top of infrared. Microwaves are low energy. Radio waves appear on top of red after infrared. So energy-wise, they are lower. X-rays appear even further down, ultraviolet radiation. So therefore, they are high energy. So there are mainly 6 radiation we talked about. Electromagnetic radiation consists of these 6. Gamma rays, 7. Gamma rays are highest energy electromagnetic radiation, which appear below UV light or ultraviolet light. Now we're going to look into these in more detail and talk about properties of electromagnetic radiation. A radiation has wavelength. It's a periodic motion that's common to waves. Periodic motion of magnetic and electrical field for electromagnetic radiation. Wavelength is called lambda. It's the distance between 2 successive peaks in a wave. It's measured in meters. Sometimes we express them in nanometers. Nanometers is 10 to the 9 meters. Nanometers is 10 to the negative 9 meters. Frequency is the mu, number of waves that pass through a fixed point in 1 second. Frequency is in 1 over second. per second. It's also expressed in hertz. Radio waves are called megahertz, kilohertz, like that, FM radio, etc. Frequencies characteristic of a wave. So is the wavelength. Wavelength of a frequency are wave-like properties of light. That water waves, which are completely different types of waves that require medium, also have wave shapes. That traveling waves on a surface used to on the beach to ride surfing is a wave. The wave moves. It has a wavelength or frequency. So when you look at the wavelength, it's the distance between successive peaks, as in the red wave. Purple wave has shorter wavelength. Shorter the wavelength, high energy, the stronger, the more the energy. Longer the wavelength, shorter the energy. So there's some relationship between energy and wavelength. One of the things about electromagnetic radiation is it travels at the speed of 3.0 10 to the 8 meters per second, called the speed of light. So all electromagnetic radiation travels at this speed. Wavelength and frequency are inversely proportional to each other. Wavelength is 1 over frequency or vice versa. So we have a wave equation that gives relationship. C is equal to speed of light is equal to lambda mu. Lambda is the wavelength, mu is the frequency. So if you look at that, we are talking about the same thing we did before, wavelength and the lambda. As lambda increase, larger lambda means shorter frequency. Shorter lambda means large frequency. So the frequency is directly proportional to energy. So this relationship, whether we are talking about lambda or mu, we can express the relative energy of two wavelengths. So we're going to look into total electromagnetic spectrum, that is everything on the spectrum. Various types of radiation seem to have different responses to our sensors. How we feel infrared is, we feel it on our skin. Where visible light, we cannot feel visible light by our skin, but we feel it by eyes. So different things. Magnetic spectrum, EMR spectrum is can be shown as on a scale of lambda or frequency. Looking here, if you look at this diagram, on the top is the wavelength. So wavelength, shortest wavelength is gamma rays. That's the highest energy. So gamma rays, X-rays, UV, visible, IR, microwave radio. Six radiations we talked about in the last slide have these lambda values. can you turn off your mic if you? It take me a while to figure that out. I had to go back to here. Let me go back. I pressed something, then went into. Okay. So higher the lambda radio waves have shorter frequencies. Lower the lambda gamma rays, 10 to the negative 14, higher the frequencies. That's the inverse relationship. You can see at the bottom expansion of visible region. Violet is the highest energy and red is the lowest energy among the 5 colors. VIBGEO. We call it VIBGEO. Violet, blue, VIP. Violet, indigo, blue, yellow, orange, red. Okay, let's do some relationship between wavelength and frequency. Answer following questions. What is the frequency light of, in hertz of green light, which has wavelength of 525? Hertz is same as 1/second. Wavelength is normally given in not in nanometers, meters. So we have to use the wave equation called C is equal to mu lambda. Then you can calculate frequency. Velocity of light is 3.0 10 to the 8. Knowing the lambda, you can plug in the values. You plug in lambda values in meters. C is 3.8 10 to the 8. So you rearrange this equation. C is equal to nu lambda, lambda nu. So C divided by lambda, that's what we're doing. C is 3.0 10 to the 8 divided by 525 nanometers converted to meters 10 to the negative. The frequency is hertz is same as seconds. Frequency of that light is 5.7 10 to the 14 hertz or per second. So how many light would pass through one fixed point in 1 minute? That is the frequency. In 1 minute, we have to find out how many minutes are in, how many seconds are in minute. 1 minute have this time 1 minute is multiplied by 60. This radiation frequency is 1/second for 60 minutes. 1 minute has 60 seconds. Then it passes 3.44 10 to the 6 times more. If it is then in 1 hour, so you calculate for 1 hour another 60 minutes, 60 multiplication, 60 times 60. That's how many light will pass fixed point in 1 minute of the same frequency, 5.74. What is meant by amplitude of a wave? There's another description of beside lambda and nu, lambda and wavelength and frequency. we also talk about amplitude. Amplitude is vertical length of a wave at different, from top to bottom of a length. If you look at the diagram here, lambda is given here, that vertical length on the side here is the amplitude. Amplitude indicates strength of the wave. Like a surfing wave, higher the wavelength, higher the wave is more intense. So intensity of a wave is given by amplitude. Amplitude is nothing to do with lambda, and it doesn't affect lambda and frequency. It's only the strength of the wave. So now we're going to look into more energy of sun. Look into what kind of radiation mainly come from sun. Approximately 54% is infrared radiation. That's good. We get heated on the heat radiation is infrared, 50%. 39% is visible light, 8% is ultraviolet. So not many gamma radiations or lower frequency radiation are given out of sun. Human eye can see only visible region. If you look at the distribution, about 100% that is somewhere around 50 nanometers, that visible region. So there are some ultraviolet above the violet color region and infrared at the lower wavelength values. So mainly infrared, 53%, 39%, and 8% UV. So that's the distribution of sun's radiation in the form of electromagnetic radiation. Now we're going to change the topic a little bit. We had a problem in the history using classical theories like Newtonian mechanics, description of large planetary bodies, equations like Newton's laws, using Newton laws, were applied to atoms and molecules. So to get the idea about how that failed, application of Newton's laws to radiation. So if you look at this object that is heated and that is glow, called black body radiation. Black body is a body that emitted radiation when heated and when it glows. The color emitted by the light is related to temperature. Higher the temperature of the black body, higher the energy, intensity of the radiation. Intensity of the radiation is normally, as you heat it up for that black, according to classical theory, as you increase the temperature goes up. The radiation intensity increases exponentially. But in practice, the blue light, green light, red light, which are different radiations, show a distribution like that is shown in the picture. They couldn't explain through through classical theory. They come up with the theory called Planck theory, quantum theory, which is E is equal to h mu. Planck constant is the h. Energy is Planck constant times frequency. You can rearrange this equation to replacing C with new frequency with C divided by lambda or so. That equation was successful explaining black body radiation. So this description came up with the idea energy of a small particle is quantized. That's called the quantum theory. So waves have both wave properties and particle properties. So radiation behave like waves, also particles. This is the part of quantum theory. Certain energy values are only allowed. Energy cannot be any continuum. There are steps up. Energy radiation is related to frequency, and so this equation explains energies of small particles like atoms, electrons, etc. Planck constant is 6.626, 10 to the negative 34. We are describing this to discuss about the absorption of light by molecules, atoms. So energy is quantized. Only waves can have, normally water waves can have continuum of energies, any amount. But on the right side, there are steps. At this level, there's only one step, not in between energies. So small particles have energies which are quantized. So we look into this phenomena about wavelength, frequency, energy in terms of quantum theory or Planck's equation. Calculate the amount of energy present in wavelength of red light and blue light. Do they have the same amount of energy? Why not? Or why not? They don't have the same energy. So we're going to prove that. Red light has 700 nanometers, 450 for blue light. If you use the Planck equation, quantum theory equation, came from quantization of energy. You use this equation in different ways. E is equal to h mu. You can rearrange to E is equal to hc divided by lambda. So red light, we have to use lambda. H mu. H is E, energy of the red light is E is equal to h mu. H is 6.626, 10 to the 34. So we calculate the red light. Energy 2.834, 10 to the negative 19 joules. Blue light, when you calculate that, 4.417, 10 to the negative 19, which is larger. The blue light has larger energy than red light. That is we seen in electromagnetic spectrum. How is energy is related to frequency or wavelength. We looking here from the frequency lambda point of view. You can calculate directly from frequency also. In the distant, not too distant past, we used to develop pictures in dark rooms. So do you remember dark rooms? If you have gone to one, use red light during the developing of pictures. Why is red light used, not other light? Red light doesn't affect the film chemicals. The blue light is high energy. That is, if you look at the picture, the blue light is not in the range 620 to 750. The blue light is 450 here. So blue light couldn't have been used. So this is something to do with the energy of the different radiation. Electrons in an atom also show quantization. This idea that came out of quantum theory, E is equal to h mu. E is equal to Planck constant time frequency as the idea of quantization. Electrons closer to the nucleus have low energy than we talked about that some time back. So energy of an electron, like a stepwise, is only allowed certain energy, quantized. Energy could be either in first shell, second shell, third shell. They have discrete energies. So when electrons jump from high energy to lower or vice versa, like in the diagram on the right, when you jump up, low energy to high energy, it absorbs energy. When it returns back to from high level to lower level, it releases. For example, if this is on excited, I'm sorry, it went back. Outermost to inner energy is released. From top to bottom, on the side, we also show this. Energy from bottom layer to top layer is the highest energy. Highest energy is UV. From second level, first level to second, third level, there are 4 levels. It's green, low energy. So energy is related to lambda. Okay, higher the lambda, low energy. So electrons also shows that kind of behavior, emission and absorption as we move electron from one shell to the other. Different element emit light at different energies due to differences in their electron energy levels. Since the energy levels of electrons are quantized, only they can have certain energies. Light energy appears to appear in lines as emission spectrum. When light emitted by atom only shows certain energies, we get line spectrums. For example, hydrogen, when absorbed by electromagnetic radiation continuum, hydrogen source line spectrum in here. That always true for hydrogen. That's a line spectrum. This is the absorption spectrum. Different element emit light at different energies due to differences in since the energy level of the quantized light emitted appears as lines in the emission spectrum. So this is really absorption spectrum. These lines are absorbed by certain frequencies. You have seen fireworks. Let's see whether you can connect different colors that come from fireworks to different emissions of light from different elements. Firework display is one of the life's most pleasurable sensory experiences. The observed colors are related to transmission of emission of light when they are burned in the flame. So fireworks are created by different metal compounds, included explosives. When they burn, the electron get excited to high level. When they come down, they have emissions of certain colors. Thermal energy from the explosives are directly converted to light energy. EM spectrum that show results in a yellow colored flame. Yellow color is characteristic of sodium, element sodium. So when you look at this yellow color, it's come down to from outermost layer to excited state to a ground state, you get emission of yellow light. For example, strontium emits crimson color. It has low energy. Low energy because lambda is higher than yellow light. So different metals have different colors. So they produce different colors in the firework. You can search on the internet what green color fireworks found in what elements is copper. What are some environmental hazards of compound that contain these elements? Copper is kind of in large amount, they become toxic. So barium also produce nice green color. Barium is a heavy metal, so therefore environmental consequences are there when you have them. So different colors are produced by different elements. All right. We're going to look into ultraviolet radiation because it's important part of sun's radiation. There are 3 types of ultraviolet radiation that comes from the sun. UVA is longer wavelength, lowest energy. UVB is medium energy. Highest wavelength, shortest wavelength is UVC, has the highest energy. Last two, UVB and UVC, are not coming to the Earth's surface. Most UVB is absorbed by ozone in the ozone layer, UVB. UVC is absorbed by oxygen in the atmosphere. It breaks up by oxygen and ozone in the atmosphere. So therefore, we had to worry more about UVA. Out of these, UVC is very small amount come to the surface of the Earth. UVB could be reaching if the ozone layer is getting thinner. Therefore, we have to worry about UVB, where the ozone hole is bigger. Okay, we're going to continue this UV radiation here. UV radiation has enough energy to cause some molecular bonds to break. Photons are the particles of UV radiation, particle distribution of UV radiation greater than 242 UVC break the oxygen bonds. Wavelength greater than 320 can break only ozone. So these three are eliminated. These two, UVB and UVC, are eliminated from the atmosphere by ozone layer and oxygen. So when ultraviolet radiation is absorbed by ozone molecule, that's 3 carbon atom, 3 oxygen atom here, the energy absorbed breaks the bond. Energy is kind of used to break away those two bonds. Then you get oxygen and atomic oxygen. Let's look at the UV radiation absorbed by skin. As I discussed before, only low energy UVA light reach the surface of Earth. So they are the one that cause skin damage. So skin damage is mainly caused by UVA. UVB is absorbed by the ozone layer. Okay, I'm going to stop at this point. I'm kind of getting tired also. You guys read the PowerPoint slides and look at the problems in the chapter 3. All right. We're going to meet on next Wednesday. All right, 1:30. Do you have any questions? Anybody about any question about test or etc.?